Saw you. Hello, everybody. Welcome. So excited to see so many people that have an interest in controls. My name is Jen De Sierra. I am a marketing specialist for VCSS. I've been with the company VCSS for 2 years. I've been with Veritech for over 10.
Hey, I'm David Dunchi. I'm the System Integration Administrator. Been with VCSS for almost 4 years. I've been in the industry for about 18 years. So today we're going to be talking to you about some controls fundamentals.
And this is all of the topics that we will be covering today. Now, keep in mind that these are very high level overviews of all of these things. We could go into an enormous amount of depth, probably an hour or more on each and every one of these. However, this is fundamentals of control, so we're going to try and hit as many topics as we possibly can. So HVAC controls for buildings, they have a lot of different names, but it all means exactly the same thing. You may have seen some of these acronyms, you may have not, but some of the more popular ones are BAS or BMS for building automation system and building management. But just know that if someone has a different flavor, then they're referring to the same thing.
All right, so let's do a history overview. So we're going to be talking through this in kind of some eras, prior to where controls really starts to enter, at least be invented, is actually in the late 1800s. And we'll talk a little bit more in detail about that. Start to take more, this basically creates the pneumatic era that lasts through about the late 1970s, early 1980s. Then we shift into the DDC era, where DDC controls are still the dominant backbone of most control systems. And now in the modern age, we're shifting more into what we're kind of calling the IoT era. So let's do a little bit of a deeper dive. So let's start with pneumatics. So the first thermostat was actually invented by Warren S. Johnson in 1883. He was an inventor and a self-taught professor. He was working at a college and he had a problem where his classrooms didn't have very good control. The way that they actually maintained heating in the building is they had a boiler system, but a janitor would basically go into the classroom, see what it felt like, run back upstairs to open or close vents to let more hot air into the space to maintain temperature. It was incredibly bad at making the temperature good, and also, and in addition to that, it was very disruptive to the classroom environment. So he took a stab at creating a device that would basically automate all these things. And I saw some source material that even indicates that the first iteration of this would literally, like, as the temperature would go below the area, it would ring a bell. So now the janitor doesn't have to walk back and forth. He just hears the bell, opens up the relevant vents. But Warren didn't stop there. He continued to perfect the system, eventually obtaining a patent in 1895 for sort of the first example of a pneumatic system, where the same system that's sensing the temperature is actually automatically opening and closing the air vents accordingly. This guy is, of course, if you recognize the Johnson name, eventually with his kids, forms what becomes, as we know, Johnson Controls Corporation. So this is kind of part of their history. But what we don't really necessarily see that this actually take traction in widespread commercial applications. It's all about the 1940s. But then this kind of becomes, again, the era of pneumatics goes from that 1940s period into the late 1970s. So without going into too much detail, how does a pneumatic system work? Well, basically, we're using air pressure to control a system. And if you have any understanding of the physics, temperature and pressure have a very direct relationship with each other. So as temperatures change, there's a pressure impact. Using those sort of laws of physics, you're basically sending signals using that air pressure network from the input devices to open and close dampers, valves, etc. The applications become very extensive. We won't get into that because we're not really, although you can still buy pneumatic products and there's plenty of buildings that have pneumatic systems in there, generally the model has shifted to DDC controllers. So we'll go ahead and transition to that. So DDC, like I said, becomes a little bit more prevalent. It starts to emerge in the late 1970s, early 1980s. And this really correlates with improvements in computing technology. This is around the era where PCs start to become out there. And what we're really seeing is that microchips and all the infrastructure associated with that start getting smaller and smaller, cheaper and cheaper. And everybody's wanting to get into this, and this extends to the controls itself. And so what are the advantages of this is that, again, this is, if you're looking at a pneumatic system, one of the disadvantages is that they're very difficult to maintain. A lot of labor goes into make sure that this pressure tube stays intact. Whereas DDC, since it's sending electronic signals, inherently the technology is going to be more reliable. Another one of the benefits is that since we're using microprocessors to control everything, all of the computation speeds is greatly increased as well. And this has impacts not only from like the visibility of the sites themselves and how you see the data, but also impacts how the functions work, how the logic works, and that increases the improves how temperature is maintained, for instance, and also the energy efficiency application. So why use controls? So I did a little bit of research and I found a paper published in 2022 by the Clean Energy Manufacturing Analysis Center of Commercial. And basically they estimate that 60% of commercial buildings over 50,000 square feet have a control system managing their HVAC lighting systems. Now, in buildings below 50,000 feet, only 13% of buildings are estimated to have any kind of control systems. So for all these people that don't have control systems, why might they want one? Well, the first one is kind of relevant to what we talked about earlier, maintaining optimal comfort. Warren Johnson put in a control system to improve the comfort conditions of his building, and that might be one of the best reasons to put in a control system in your own building. If you don't like going to thermostats and manually adjusting those accordingly, and you want to consolidate that and automate all of those processes, well, that's where a control system can do a lot of work to help out there. So the second part of it is energy management. As we noticed in the acronym explanation, a couple of the ways of referring to a control system is an energy management system. And the reason is that in automating all the processes in your mechanical and lighting and various other building systems, you have a lot of opportunity to optimize the actual performance of that equipment. And so, when used correctly, a control system should improve the energy performance of your buildings. A lot of times when contractors like ourselves go to a customer, we're looking at their utility bills, we're looking at their equipment and how much energy they're consuming, and we can often calculate a reasonable projection of how much money per year in utilities our systems are going to save them. And so the customer has a good idea of, hey, I got to make this investment and this is how fast it's going to pay off. It's a big driver of sales in our industry. So the last thing I want to touch about on why controls is indoor air quality. This is an emerging trend, especially in the post-pandemic era, where people are considered about the health of the people inside of their building. And a control system can help a lot with this because we can measure different metrics of, like, for instance, CO2, particles, and VOCs. We can measure those and then use that information to drive and optimize ventilation to make sure that we're not only achieving energy efficiency and comfort, but also taking the actual indoor air quality into account.
Okay, so with that, let's look at what a general system architecture for controls is going to look like. Now, keep in mind that not every single building will necessarily look exactly like this. And you may even have where certain layers do double duty, like a field controller may also serve as a supervisory layer. That being said, this is the general idea of how we would structure a BAS system. Starting from the bottom to the top, pretty much with the least complex to the most complex in terms of this is the hardware, this is what I can see, into the more theoretical and the analytics. We have inputs and output layer. We have field controller layer, supervisory layer, and then finally the server layer. And as you see, you can't really have the server layer without the bottom, just like you would in a pyramid. So let's start with inputs and outputs, otherwise referred to also I/O layer. Now, this is where the action happens. This is a very basic look at what is happening here. You have inputs in the form of sensors that are picking up information, they're feeding it to a controller, And then there are outputs that are then controlling for a specific goal. So let's think about, not just in this, but in control systems in general, how does your body sense what's going on around it? Well, it's the five senses. You have hearing, taste, touch, and all of those sensations are brought in by those different parts of your body. So you have your eyes, your ears, your nose. Control systems are really no different. The only difference is that they're measuring different things. So sensors, which are what inputs are, measure pressure, temperature, humidity, CO2, VOCs. There's a whole host of different types of metrics that we can look at and we can search for within an environment and then control for. Something that is very, very important to ask yourself when you are looking for inputs and sensors within a space is, what and why are we measuring something? Am I trying to measure temperature? Am I trying to measure humidity? I mean, it seems pretty simplistic, but you want to use the appropriate device for what it is that you want to measure. And that also plays into sensitivity. How low of a pressure or how little of humidity or how low is that VOC in the environment that we want to be able to sense? And then also the size of that. And an example of a sensor where size would be important is a temperature sensor within a duct. So you wouldn't necessarily use a tiny little probe sensor in that space if you were putting it into a giant ductwork, because it's just not going to be able to measure what's going on there. And then we will move on to where. So where something goes is also just as important. So if you were walking into a giant room and there was a wall of windows, where logically would you think that you should be putting your temperature sensor?
Right by the window?
That would be wrong. It would be somewhere in a space where it's a little bit more even, because you want to make sure that you're picking up the true temperature of the space where people are going to be moving around, working, doing what it is they need to do, instead of putting it right next to a window where there might be direct sunlight that's coming through. That's going to cause your equipment to run a lot longer than it should. It's probably going to cool the space down way more than it should as well, which is going to result in comfort issues.
I guess for that reason, I shouldn't put it right behind like a refrigerator, for instance, right?
No, because it's going to be too warm.
Oh, darn. Okay.
Or in the refrigerator.
Yeah.
It seems very simplistic, but these are things that are not always taken in account when designing systems, when installing systems. So keep that in mind. And then the other half of this, when we've put the inputs into the controller, we have to actually do something with it. If it's not adding up, if it's too cold in the space, well, we got to heat it up. How do we do that? We do that through outputs. And there are a few different examples of that. We would have relays, triacs, actuators are a big one. And what outputs are doing is they're taking one form of energy, whether that be electricity, if that's in a DDC system, or pneumatics, or thermal, or mechanical, and we're turning it into an action. So it's a little bit magical seeming, but it's all science. And to get even more granular with inputs and outputs, there are two different types. So we have digital or binary, that it's referred to particularly on the software side, and then analog. So binary, as you can see in the photo, it's like a light switch. We're turning it on or we're turning it off. And an example of that within an input would be a fan CT. It's sensing whether the fan is on or whether the fan is off. There's nothing more complicated to it. And then an output example would be a relay. It's turning the fan on or it's turning the fan off. Real simple. Analog is a little bit more complicated. It's reading variances in magnitude or scale. So if you can see there, there's a knob. We have more control over it. You would see this particularly with temperature, pressure, humidity, VFDs. An example of it would be a temperature sensor. You can't turn temperature on or off. Temperature could be 50 degrees. It could be negative 1000 degrees. It could be 200 degrees, hopefully not, but it's on a scale. We don't read it as on or off. And an output would be a VFD, or a variable frequency drive, which is controlling the amount of CFM, or the speed at which the fan is moving. So this is great for energy efficiency. Analog is a little bit more complicated, but you're measuring all of these things with voltage, amperage, and resistance.
Cool. Next, let's get into the field control. This is where our inputs and outputs are ultimately going to and coming from. These are the workhorses of our control system. The field devices are really handling the transition also between hardware and software side of what we're doing here. So it's going to basically take all of our input data, use the software inside, and then drive the output according to gain the desired result. So here we're looking at, a basic controller layout of one of our field devices. On the left side, we have inputs where we're gathering the data. Right side, outputs where we're trying to do things with. And let's zoom in on a particular section of this particular layout to kind of demonstrate how this works. So what we can see here is we're trying to maintain humidity in a space. So what we need to know is how humid it is in the space. And we're going to do that with our analog input, which is humidity sensor. It's going to tell us relative humidity as a percentage. And then inside of the controller, we're going to have logic that is going to basically drive the output based on what's called a set point. Set point in this, let's just say an example that our humidity is 35%, but our set point says we want it to be 40%. Well, how are we going to raise the humidity? Well, we have an output that is actually linked up to a humidifier command, which is a DO on and off. So what the programming inside the field controller is going to do is it's going to look at the temperature relative to the set point and say, hey, I need more humidity. I need to command the humidifier to turn on. It is going to turn the humidifier on. And if the humidifier is working properly, it'll slowly bring our humidity up until it satisfies that set point. And once, the sensor realizes that, it's going to go ahead and release the output. And we're going to coast there until the environment doesn't match the conditions that we want to see. So another thing I want to talk to you while we're on this subject is different controller types that you might see. And we're gonna split this into two categories. And the terms that are associated with this is free programmable and pre-configurable. So with the free programmable device, you're basically buying a piece of hardware that is basically a blank slate. It's on the controls contractor to do all of the programming within that device, test it, make sure it all works properly, and implement it. The difference, and then on the pre-configurable side, the device actually shows up from the factory with the program already intact. And what it's instead going to present to the field technician who's setting up the device is a series of what usually looks like a checklist. And that checklist is going to have options like, is there an economizer on this unit? Yes or no. Is there a return air fan? Yes or no. A discharge air temperature? Yes or no. And the technician's going to look at their current application and they're going to check all the boxes that apply. And the internal programming is going to run to maintain as expected. So why would you use one versus the other? Well, the most clear example is that free programmable is going to allow a controls contractor to do things that are a little bit more specific, custom. And this is going to apply to things like central plants. It's going to apply to complex air handlers. You're just not going to see a pre-configurable controller that's really going to address all the nuances of different systems like those. Pre-configurable, on the other hand, that's really going to come into place where you have a lot of the exact same type of unit. We're talking VAVs, we're talking heat pumps, smaller units and smaller applications where you don't necessarily need to spend all this extra time. And that's also one of the benefits of the pre-configurable controllers. It's generally going to be a cheaper product, and you're also spending less labor doing the whole checklist option thing. Now, there's also a little caveat there is there's a lot of controls contractors that don't use any pre-configurable despite the benefits that I've articulated. They have a robust programming team and they've devised strategies that are still copy pastable to an extent, and they're still utilizing free programmable devices. Again, you have a lot of flexibility in those devices to do custom things that even outside of just the basic sequence of operations we're trying to achieve in a building might allow a controls contractor to tailor the system more to what they're selling and what, it could have a lot of implications of how a controls contractor goes to markets.
Okay, we're moving on up to the supervisory layer. So, just as you would imagine, a supervisory layer, they are supposed to take all this information like you would in an organization. You have all these different people that are bringing things to a supervisor, and their job is to make sense of it and then to drive some sort of result. Supervisory layer is really no different. Another example that I would use is pictured here. So a sorting facility, imagine there really wasn't a sorting facility. It was just a bunch of boxes. Imagine you didn't have any sort of, whether it was people or automated systems in order to make sure that those boxes are sorted and coupled with the appropriate drivers. Those drivers were put on the correct route. Imagine none of that. It would take a considerable amount of time for all of those boxes or information to get where they needed to go. And you'd have a lot of angry customers, a lot of frustrated drivers. And so a supervisory layer hopes to, does alleviate that. Along with that, communication trunk management comes all the things that you can do once that data has been made sense of. So you have trending, such as I want to see what this particular temperature in this room was doing a month ago and everything in between. Scheduling, I want to make sure that that temperature does something on this date at this time, and I want it to happen every third Wednesday of the month. And then on top of that, because we understand what the system is doing and how all that information is supposed to flow between those inputs and outputs and controllers, we can then have alarming. So we can notice when something maybe might not be right within a space, and we can set that up so that it notifies someone right away. There's a lot of global logic that lives within these, meaning it's logic that pertains to all of these pieces of hardware. And occasionally, especially if it's on a smaller scale, you're going to have some flexibility for user interfaces or how you can see that information. I want to see it charted. I want to see what that looks like in a way that's not just a bunch of numbers.
Awesome. So now let's get into the server layer. And as Jen suggested earlier, a lot of the things that the server layer does, the supervisor layer also can do it. But where we're getting into the server layer, where this is going to come up is in a larger building where you have multiple supervisors and you want to consolidate the data and therefore the user experience. So in the server application layer, like I said, we're consolidating things. And so we can basically, instead of a user having to log into various supervisors to see the aforementioned trends, graphics, schedules, and all that, we can create a single place where they interact with all this stuff. And another term for this is also the client. So again, larger buildings, we're going to basically say, go to the server layer, log into this single point, you see your entire building, everything is nice and consolidated. So let's talk a little bit more about some of the components that might go into a client layer. And again, the caveat still applies. A lot of these things can exist in a supervisor, especially in smaller buildings. But we're going to have our graphical user interface. And what that's going to usually be comprised of is you're going to see things like floor plan images of your building. It's going to show where your equipment is, which areas they're serving, what the conditions of those different areas are. So that way, an operator looking at it can know exactly where the hot and cold areas of their building is, where are the problem areas, where am I, when I grab my ladder, where am I going in the building? And those are kind of the main things you see. You'll also see some equipment pieces of graphic that'll basically show in detail what the equipment looks like, how it is operating, all the key metrics that you might need to see to understand, yeah, this is working, or oh no, this is a problem. I need to look specifically at this component. And again, a nice consolidated place to view all of your trending and your schedules. is a great way to save operators time. And that's time in terms of moving around to the building to see these different pieces of equipment, and also just time sitting at the computer clicking through these different objects.
All right, so we have the groundwork laid. We know what the layers look like on a control system, but how do all of these devices speak to each other? Well, they have to communicate somehow, and that's through either wired or wireless communication. And these are three of one of the main methods that you're going to see in order to reach those goals. The first is going to be master slave token passing, or MSTP. And this is a very standard style of wiring within the controls industry. It's mainly that way because it is a two conductor and it is daisy chain. So it's very simple to install on a device. You just, as you can see here on the little the image there, it goes from one to the next to the next. There is no intercommunication. It's daisy chained. So the only problem with this is that it can be a bit slow. But that is solved with Ethernet over IP, or Internet Protocol. So you might recognize these cords. They may be a little bit familiar because Ethernet over IP is used for a vast amount of other types of building systems and IT systems, and people are gravitating towards it quite a bit in the future, despite the fact that it is a bit more costly in material as well as labor for MSTP. That being said, communication speeds are considerably faster, and with mirroring those other systems, you have a lot more potential for scalability in a building, as well as if you're looking to create a smart building in the future or at present, or matching Division 25, which we'll talk more about later. There are three different types of Ethernet that are most pervasive, but the ones that you will see in controls most often are Cat5 and Cat5e, which stands for enhanced. And then finally, we have the wireless solutions of the world. So wireless is obviously a little bit different. It's still in its infancy, but it does work very well for retrofits as well as smaller buildings where you really don't want to put forth all the time and material to wire from place to place. You can just make sure that it's secure to the wall, and then it will communicate with other routers as well as other thermostats within that space or that larger building. There are a couple types of protocols within wireless. Well, I'm actually sure there are many more, but the primary ones you might be familiar with are Ecobee or Zigbee, but they all essentially act the same. As you can see there, they are wireless mesh networks, which is something that you see in other IT solutions as well. What it does is it serves as a mesh. Well, what does that mean? So all of these devices, they are not like an MSTP where you're reliant on all of those devices to communicate because they're wired one right after the other and sequentially. Wireless thermostats and devices, they will bounce around. So we have two devices. This one sends a piece of information in order to get something accomplished to this one, and then it bounces from each one until it gets where the message needs to go. And so the benefit of this is if one of those devices goes down, that other device can then send it to another device and then another device. So there is that healing quality to it, and so that you can address that issue with that other thermostat without actually losing communication to your entire system. The devices themselves are usually more costly, but like I said, labor is less intense.
What about building conditions? You gotta keep in mind on a wireless system.
It's going to be really tricky if you try to install a wireless system in a building that has very specific materials that it's made of. So if you have a very let's say, secure site where the walls are made of 5 feet of concrete or very thick metal, that communication is more easily disrupted. So there are some ways around that by adding more routers. But really, in actuality, there should be a different approach taken, a wired solution, in order to ensure that that communication is actually happening and that you're not getting a bunch of calls. A customer is not getting frustrated in the long run. So now we found the way that these devices communicate with each other. So what is the language? It's like I have all the parts to speak. I have lungs, I have vocal cords, but I actually need to speak a language. And that's what protocols are. They're languages. In the industry, you'll see proprietary as well as open. We're going to review some of the main benefits of each one of these. Proprietary being they're not open because they might have unique communication speeds at which the information is traveling over those wires that we talked about, unique data formatting. There's a lot of different features or factors that go into why a protocol or language might be proprietary, which is this one particular manufacturer, they own that, and it doesn't communicate with other systems. That being said, they do have the ability to be specially designed because you have a team that is dedicated to making sure that their product stands above the rest. How do they differentiate? They're going to pour a lot more interest into trying to be special. They're going to come up with features that nobody else is going to have to allure. And then they have a more reliable communication network. In theory, think of Apple products. An Apple iPhone is probably going to speak a lot better to an Apple TV and transfer that data back and forth as it would with an Android, if it's even possible. And then enhanced functionality. So you have teams dedicated, again, to supporting that brand. Their reputation lives on the line. Then that being said, other products do as well. On the open end, you have way more flexibility because you can have multiple vendors under one roof. And we'll talk more about this in the next slides. But I could have a KMC, I could have Reliable, I could have Siemens, I could have all these different brands, and they all are speaking the same open language. And they can all live under that one roof. So a customer does not have to completely rip and replace their entire system in order to get some more improvement or get out of vendor jail, what we like to call it, where you don't have that ability to go somewhere else and get your system serviced. And then piggybacking on that, we have vendor choice. So even extending into the equipment itself, a lot of manufacturers, they include the ability to get backnet cards, which essentially allow you to pick and choose what type of control system you want to work with. So you're not pigeonholed into one. And then finally, standards. Anyone and everyone can collaborate on this because it's not being guarded by that trademark. So you get a lot more information, a lot more collaboration that happens with these protocols. To elaborate even further on that, all of those features that proprietary protocols have, if done correctly by a controls contractor, can be achieved with open protocols as well. So what are some open protocols? Well, let's start with the two that maybe are not as pervasive, which we have LawnWorks, which is a peer-to-peer that was initially developed by Echelon Corporation. And then we have Modbus, published by Modicon, which is now Schneider Electric. They did that in 1979. And it was used with programmable logic controllers, or PLCs. And that's primarily what you're going to see Modbus applied to today. All of the other controls that are open, it's going to be BACnet. And here and in really in the industry, it's a standard, it's the king. And a little background on BACnet itself. The controls industry started off as proprietary was everywhere. It was a little bit more of the Wild West. Every single manufacturer had their own proprietary protocol, and none of those protocols could speak to each other. So when someone sold to a customer and that customer then installed that system, if anything went wrong, then they couldn't go anywhere else to another manufacturer to get help because they didn't have the tools to work on those because it was safeguarded by that original company. And in 1987, BACnet was created by a group of ASHRAE members who realized that there needed to be a standard and there needed to be an open standard. And something to note as well is that BACnet stands for Building Automation Controls Network. It seems like a bit of a generic term, but I think that that fits very nicely into it's accessible to everyone. And it's what we really believe in and most do in the controls world. So let's say that you have a building that has all these different open and proprietary protocols living under the same roof. Well, you would have to log in to each one of those different systems, even if you had one thermostat going to one controller to one actuator. You would have to log into a system in order to see that one little room. So there are things called protocol translators. And one example of that would be a JACE. It's very common, called a Java Application Control Engine. And what it does is serves essentially as the Rosetta Stone of controls protocols. You can take all of these different languages and they all, instead of speaking French, Spanish, Italian, they're all speaking that common universal language. And that makes it a lot easier for retrofits, for someone to make some sort of migratory transfer into using another vendor. Yeah.
All right, so let's get into sort of the functions of software that are running devices. And this is kind of getting back into our field device layers. That's generally where these control loops exist. And first I want to just kind of make the most common metaphor for what a control loop could be. Usually when people are trying to describe it in layman terms, they're going to use the example of driving a car down a highway. So what are you doing? You're either trying to maintain the speed limit if there's no traffic, or if there's traffic, then you're trying to maintain an acceptable distance between you and the car in front of you. I know that's definitely true here where we live in Phoenix. Everybody's doing that. But anyways, what are you doing? You're looking to see what's the visual information of the car in front of you. For instance, you're speeding up and you're slowing down to maintain that safe gap. So what you're doing internally basically is you are running a control loop in your brain that tells you how to use your feet to use the accelerator and the brake pedals. So let's take it out of the metaphorical and take it into a pretty common HVAC controls application. And we're going to go through this by defining the various terms of the important components that make up a controls loop. So we're going to start with the control variable. This is an input device going back to the I/O side of things. And in this particular example, it's going to be a temperature sensor. So we are both using the temperature sensor to understand what the temperature is, but it's also our guiding point of how do we refer whether or not we're doing the thing we want to do. So next up in that is, again, that thing we're trying to do, it's going to be the set point. In this particular example, we're going to say that the set point is set at 75 degrees and that the control variable is currently at 78 degrees temperature. So from there, moving through this, we could get into the deviation. And the deviation is basically going to be the difference between where your set point is and where your control variable is. In this case, we have 78 degree temperature and a 75 degree set point. That gives us a deviation of 3 degrees. So that is ultimately going to relate to how severely we respond to control the loop output. In this case, this is going to be a chilled water valve. It's going to open and close. based on how large our deviation is from the set points. And one more term to throw in there is a deadband. Now, let's just say in this example that we're not at 78 degrees, we're at 75.1 degrees. I don't necessarily need to start opening up my chill water valve. That's where the deadband comes in. This is especially useful for maintaining the life of your systems and kind of just generally smoothing out the edges of how this device works. So let's say, for example, the deadband for this particular situation was set at 2 degrees. And that's going to be a bidirectional function. So we're basically going to say whatever our set point is, the deadband is going to be plus or minus 1 degree to achieve that total of 2-degree deadband. And what that means is in this particular scenario, we're going to wait until the temperature gets all the way up to say 76.1 degrees. We've exceeded the deadband. Now the loop can actuate the output to start bringing the temperature down within tolerance. And it's going to probably continue to do that. And this is especially going to be true in things like a compressor where we're staging it on and off. But we're going to basically keep that function, that output running until we actually bring it a little bit past the set point. And that's where the deadband, and basically one thing that you can kind of consider is that in the range of the deadband, the controller output isn't really, the loop is not responding at in that range.
And that keeps everything more comfortable because you're not waiting for things to get ultra warm or ultra cool in order to turn it on, but also saves on runtime because you're not immediately turning things on and off. So there comes that energy efficiency that controls is trying to manage.
We're always trying to balance between efficiency and optimal comfort, to your point. Mm-hmm. Exactly. So let's talk about a couple of different types of loops. Generally, these are referred to as open loops and closed loops. And I tend to refer to these almost as complete loops and incomplete loops. An open loop is a loop where basically we don't have the feedback of the thing that we are actually controlling to. So this might be a situation where for whatever reason, we don't actually have that room temperature sensor in the space to tell us whether or not we've gotten too hot or too cold. Where this usually comes in application in retrofits, where you don't have a complete you haven't done a complete takeover of the building and you have limited information, but you're just saying, I want to run, like for instance, a boiler from 8 o'clock to, for a fixed period of time. We'll just say that kind of thing. And it's just going to kind of run absent-minded to whether or not it's actually maintaining the proper conditions. It's not really a great situation, which is why I'd like to pivot over to the closed loop. Now, this is really going to be a vast majority of the loops that are out there in the field. The one that we talked through earlier involving the chill water valve and the set points, that is an example of a closed loop because we are getting the feedback that tells us whether or not the loop's action is having the desired effect in the space or condition that we are trying to achieve. So now let's go into a couple of the control loop types. Because we can use loops to manipulate various different types of components, and that's going to relate a lot to, for instance, our binary versus analog that we covered earlier in here. So what if we had a binary function that we are controlling with a loop? Well, we're going to basically use a binary style of loop. What it's going to do, let's say we have a rooftop unit that has a compressor and all you do is stage it on and you stage it off. Well, that's where this is going to come into play. It's still going to measure temperature versus the set points. And as we get outside and our deviation gets big enough to call for that compressor to turn on, it's going to flip it to an on state and it's going to leave it on until that temperature is satisfied and turn it back off. Pretty straight. That's the general application you're going to see something like a binary loop associated with. And so moving on from there, we're getting into floating and modulating. These are the most common application that I'm going to kind of refer to here involves valve actuators. And floating and modulating are different ways to sort of achieve a similar result. So a floating actuator is really going to be using a combination of timing and open and closed signals, which are going to be two distinct binary outputs. There's going to be a binary output associated with your open command, and there's a binary output associated with your close command. And so let's take, for example, that chill water valve we saw in our earlier example. If this had a floating style actuator, it would have the correlating open signal and closed signal. And you would also look at, and you would basically see, hey, this particular actuator has a 90-second drive time. That means that if it's completely closed and I want to go fully open, it's going to take 90 seconds thereabouts for it to get there. And so our program to make a floating loop work properly, we're going to take that into account because say we want to achieve a 50% open valve, well, we're going to send an open command for 45 seconds. And, ultimately using that similar idea, that's where we're going to be sending the commands to the open or close to achieve a relative position of, for in this case, a valve position as it is needed to satisfy the temperatures. So the problem with the floating, there's some advantages to a floating strategy, and it usually involves costs. The components associated with floating are definitely much cheaper in a lot of cases than a modulating component. The problem is going to be a lack of precision, and it also takes up a little bit more outputs. We have 2 outputs instead of 1 output, like we'll see later in a modulating application. But because one of the inaccuracy things is again, that timing that we talked about earlier, that 90 seconds, that isn't always going to work out exactly that way. It's not as precise as you might think, and you end up developing with something that's called drift. And that's to say that by the end of the day of it opening and closing based on that time position, it might say it's at 50%, but it's actually at like 40%. Pretty close, but over time, that drift gets bigger and bigger. There's strategies, ideally on a daily basis, you should set it back to what is a true zero value. So at the beginning of every day, you start at a relative point of accuracy. But again, it's not as precise as it could be. And thus, the energy impact that it can have on a site might not be as optimal as you would like to see. So that's where the modulating situation comes into. And modulating, I think of as a lot more of a direct correlation between the output and percentage of the loop and what the physical device is doing. So again, going back to our chill water valve, if we had a chill water valve that was a modulating or took a modulating command, it's probably looking for a command that looks something like a 0 to 10 volt DC signal. It's looking for that voltage also to be persistent. There's no time basis for this. So, and you also will see like things like 4 to 20 milliamps, 2 to 10 volts, 1 to 5 volts. But for simplicity of math purposes, let's just stick with the 0 to 10 volt application. And you're going to usually see a pretty direct correlation. If I want that 50% valve position, I'm going to send out 5 volts VDC or 50% of that total signal range, and the valve is going to move to the corresponding position. And that persistent value is going to basically always be moving up and down accordingly based on the output of the control loop. So kind of getting into the weeds on some of this stuff. Again, we could talk about this for hours, but that's the basic overview of what control loops look like and what their applications are.
Right. So now that we have pretty much learned all of the basics, very high level overview, let's take a brief look at where is the industry and where are controls going in the future. So smart buildings, as David pointed out to me, have been around. The concept has been around for quite a while, but you're going to see it more and more lately. So let's talk a little bit more about what they are. Traditionally, information technology and operation technology live separately. So operational technology, as you can see there, is things actually accomplishing something. A controls system has a very specific operation that it's trying to achieve, and IT is a little bit more theoretical. It's wrapped up in the data and how does information move around. Well, with smart buildings, and specifically something called Division 25, we have integrated automation, and that's bringing both of those two worlds together. So what that means is we're not just trying to maintain the status quo or even just get better at energy efficiency throughout our control loops. We're trying to get more complex, and we're trying to use all of the information that we have in order to save energy and actually drive business results. So what is a smart building? It is integrated automation. You're going to be taking all these different systems like HVAC controls, lighting, security, irrigation, whatever it is that you could possibly think of, access control, and you're pulling it into a single cohesive network. And it's a very complicated thing to do, but this was initially brought up by the American Institute of Architects, the AIA, and they see this as being the future, and it gives a lot of security to building owners in order to actually, again, drive their businesses and save more energy and some other topics that we'll talk about as we keep going. So what's an example of what you could do with a smart building? And forgive me, my graphic wigged out on me. So, so let's say we have an access control system and it's a weekend and we have a couple people badge in. Well, we would, through our integrated automation, signal the HVAC to then turn on. Let's cool the space. We have people in the building. But then let's just imagine that it turns on and it's actually warm air. Something's not working, like either the chilled water valve is not turning on or something is wrong in the system. Well, another integration that we could have is work order management. We could bring that in. So we have this very purposeful and very unique and custom solution to a problem that's not only saving energy, but it's also saving the time and the prioritization of the employees that are charged with taking care of that building.
Yeah, so you're saying that basically that link to the work order management system, it can send out a specific work order for, you know, a job.
Generate that ticket
Yeah.
so that then that issue can be addressed as soon as possible. If it, let's say there were access cards that were opening and it was an event that was impromptu. I don't know how often that would happen, but maybe it happens in some circles. That would warrant an actual ticket being generated because maybe that is a space that only gets used when there is an event. Like there are so many different layers to this integration that can happen, and it's very, very it's very useful, but it is not something that we're seeing a whole lot of maybe on this scale. The most that you're going to see, I think, in most systems is your HVAC and your lighting and occupancy are tied together.
Yeah, that's pretty standard.
Yeah. So why would we be shifting from smart into a more smart building mentality? Well, the same way that we shifted more from pneumatics into DDC might in some ways collide as far as like we're increasing comfort even further. We're having to do less effort and we're being more proactive in protecting that comfort level and that energy efficiency. But in addition to that, we're also getting more data, and you'll hear this a lot, more data, more data. The world is so wrapped up in IT and what can we do with it? But the data is a means to actually create analytics and optimizations so that we can then even more enhance comfort. So outside of even the last example that we gave, there's even more proactive things like functional testing, fault detection that we can pour into these systems and make them truly smart. So I want to talk a little bit about why there's hesitation about Division 25. I'm not even sure how many people on the call even know about Division 25. With controls and HVAC, it's usually Division 23. And nobody knows what this is. And I think the two top reasons, the lack of awareness as well as a resistance to change, are probably the primary reasons why people don't know about Division 25 right now. And all that is going to be is normalizing it further. And then the bottom two, we have fear of complexity as well as unclear implementation guidelines. Those, as more people learn about what Division 25 is, like you hopefully have today, will be the driving hesitations towards actually implementing it. Because as you can see, if you were to try to make these things happen, they're very complex and you need to lean on master systems integrators. You need to plan, you need to utilize APIs. There's so many amazing things that you can do now, but that people will definitely have some growing pains in the future.
All right, so that gets through our presentation, and I just wanted to close out with a couple of practical points to close. And a lot of these are kind of getting at the same thing you're going to find, but these are, I'll give you my perspective just sort of based on my experience in the industry and things that I think are nice takeaways to have about the difficulties of controls implementations. So the first one I think really applies into the engineering design community, and the guidance is basically, especially in modern days, you're looking at a sequence of operation or a control spec diagram, and you're seeing a lot of copy paste these days. And the problem with this is, while it might save some time, a lot of buildings are generally going to be unique, and it is important to do the due diligence to make sure that our designs are actually meeting the the performance goals of a particular building. So that's the first step. Another thing is, a perception about what controls is, as we've kind of discovered, it's becoming, it is more already than just, running wire from one cable to the other and you're done. There's a lot of moving pieces in there, and that complexity is increasing and increasing. We're always, as a controls contractor and anybody else who's in the industry, one of the most true things that kind of comes up is like, you're always learning something new every day. There's a lot to this industry. And you're going to find that the people involved in it are generally pretty passionate about it because of that aspect. So how do we achieve some better results? That's kind of where these next two come into. And I think there's two aspects of this. It's involving the owner in the conversation when you were designing a control system or setting up a project, involving the owner as soon as possible to get their direct feedback. I've had a lot of experience with situations where you're doing some kind of a construction project, you do all this work, you do it per the plan and spec, and then when you go to train the customer on the system together, you find out that there's some things that they might have wanted that were missing. Well, at that stage, it's very difficult to react to in a way that is either cost effective or even just plain achievable. Mm-hmm. So obviously involving the owner, again, we have a lot of complicated things that we're talking about. It's kind of on the controls contractor to boil this down into plain English as best as possible to get good feedback from the customer and make it actionable. And, and that kind of feeds into the last thing, which is also make sure the controls contractors or, that you have a good controls resource when you're developing your buildings. Get that done as soon as possible. Make sure your goals are achievable. What are the means to achieve it? So make sure that the selections actually match the end goal. And those are kind of some of the big things that I've kind of seen over the years. And, just sort of speaking to the why you want to do some of these things to have a great successful result with a controls installation at your site. And with that, we'd really like to say thank you so much for all of your time. We're happy to switch into questions. I know we're at the end of the time. We're happy to stay along and hang out with you for anybody who has any questions. But if you have anything you want to type out and stuff, we'll obviously get back to that in writing after the fact. So again, thank you so much.
Yeah, thank you. We appreciate your time.
Thank you guys. Thank you guys. We did have one question pop up in the chat, but Garrett answered it in the chat, but I'm going to read it out loud just in case people didn't see it, just so we
Garrett always knows the answer, so it's perfect.
I know, it was perfect. Can you use a JACE for BACnet IP and BACnet Ethernet protocol? He said yes.
Well, I'm hoping he answered yes.
He did. He passed the test. A JACE is capable of communicating in many different protocols, including BACnet IP and Ethernet.
Excellent. Thanks, Garrett.
And that's the only question that we, oh, nope, just kidding. I lied. One just came in. Would it be, oh, just kidding. That was a question for me. As for the slides, we're actually not going to share the slides, but I am going to share the video. But if you have any more questions like slide related and you wanted to see more, Jen and David can absolutely work with you on that offline, but we're not going to post them on our website or anything. So
yeah, this is a fun conversation. We love chatting about it, and consider that an open invitation to continue this offline.
Yes,
we're happy to chat.
Yep. No questions coming through. Just saying, good job, guys. And
thank you,
you're so good at explaining. Thank you.
Awesome. Well, thanks again, everybody, and appreciate your time on this webinar Wednesday. And I hope you have a great rest of your day.
Hope if you have any lunch yet, enjoy it.
Yeah, that's what we're gonna do next.
Awesome. Thank you guys. And thank you everyone that joined us. Look for an email from me for PDHs. Before you close out, just check the chat real quick because there were several of you that I messaged because I couldn't figure out who you were. So if you need a PDH, make sure you let me know you were here. And look for an email from me, and we will see you again next month. Thank you.
Thank you.
Awesome. Bye-bye.
Bye.
Bye, everyone.
Bye.
Let me look at let's meet our